Inside almost every electronic device you own, your phone, your laptop, your car, there's a tiny component doing one of the most important jobs in the circuit.
It's not the processor. It's not the battery.
It's the capacitor, and by the end of this video, you'll know exactly what it does and how to pick the right one for any project.
A capacitor is a passive component that stores and releases electrical energy. At its core, it's just two conductive plates separated by an insulating material called a dielectric. This is what that dielectric actually looks like inside a real capacitor. Apply voltage across those plates, and charge builds up, creating an electric field. That field is where the energy gets stored. Capacitance, measured in picofarads, nanofarads, or microfarads, tells you how much charge it can store. Voltage rating tells you the maximum voltage it can handle before it breaks down. Some capacitors, like electrolytic and tantalum types, are polarized. They must be installed the correct way around. Equivalent series resistance, or ESR, is internal resistance that affects performance at high frequencies. And leakage current is the tiny amount of current that sneaks through, even when it's fully charged. On a schematic, non-polarized capacitors are drawn as two parallel lines. Polarized ones get a curved line instead. Learning to spot these symbols fast will save you hours reading circuit diagrams. Electrolytic capacitors pack high capacitance into a compact cylinder, perfect for bulk energy storage, but sensitive to heat. Film capacitors are non-polarized and excellent for audio circuits where low distortion matters. Tantalum capacitors are compact and stable, but they can fail catastrophically if you push them too hard. And supercapacitors store enormous amounts of energy, charging or discharging almost instantly. Polarized capacitors must go in the correct direction. Non-polarized ones can be installed either way, ideal for AC signal paths. Get the polarity backwards, and you risk leakage or outright failure. So what jobs do capacitors actually perform? Energy storage, filtering, signal coupling, and timing. They absorb brief bursts of energy, and they smooth out ripple in DC power supplies. They also couple AC signals between circuit stages, while blocking unwanted DC. And in RC and LC networks, capacitors shape timing and frequency, building oscillators and time delays. This DC blocking, AC passing trick is critical in audio, RF, and mixed signal design. Here's a real example. A tiny 0.1 microfarad ceramic capacitor sits right between the power and ground pins of a microcontroller. This is called a bypass or decoupling capacitor, and it's doing critical work. When the chip switches states, it creates sudden current spikes that cause noise on the power line. This capacitor acts as a local reservoir of charge, reacting to those spikes faster than a power supply farther away on the board. Engineers often combine capacitors of different values, like 0.01, 0.1, and 10 microfarads, to cover a wider range of frequencies. In power supplies, large electrolytic capacitors smooth out ripple after AC gets converted to DC. Smaller ceramic capacitors near the output then filter out the remaining high-frequency noise. In HVAC systems and pumps, start and run capacitors shift the voltage phase between motor windings to get the motor spinning. In audio systems, film and ceramic capacitors couple signals between amplifier stages and suppress unwanted noise. And when you need extremely fast charge and discharge, like regenerative braking or memory backup, supercapacitors take over. When choosing a capacitor, pick a voltage rating at least 20 to 50% higher than your expected operating voltage. Match the capacitance to your circuit's needs, check the tolerance, consider ESR, and confirm the temperature range. One common mistake, assuming bigger capacitance is always better. It isn't. Oversized capacitors can cause slow response or startup issues. Even the best capacitors wear out. A bulging or swollen casing is a classic sign of internal gas buildup. Burn marks or discoloration point to overheating. often from current surges or excessive ESR. Engineers test for failure using visual inspection, ESR meters, and capacitance measurements. From smoothing power in your phone charger to firing a camera flash in an instant, capacitors are the quiet workhorse of every circuit. If this helped you understand capacitors better, like this video, subscribe for more deep dives, and tell me what component to explain next. If you'd like to keep learning new things, you're always welcome to follow Core Successor on YouTube. Thanks so much for watching.